All right. So today, our goal is to continue the theme of the previous lecture. Previous lecture, you remember, was body plot lecture. We considered how to ascertain, how to estimate systems' steady-state response to a periodic system, right? So let me put it in a little bit of a perspective. So obviously, we're not talking about how to solve, let's say, differential equations, right? So that is like not that's not the what we mean by a response to a periodic system, a periodic signal, because to solve a differential equation, we would need two components. One is a general solution, which roughly speaking has to do with initial conditions. Another component is a particular solution that has to do with a input that is for linear differential equations. That is not necessarily what we are discussing. What we're discussing is how a system responds to the input after the transient period, so is the effect of initial conditions, goes away. Simply for conceptual purposes, you can imagine that we're dealing with zero initial conditions, or we don't care about the initial conditions, whichever way it helps you to conceptualize. But mathematically, what we were doing was we were considering a signal, right? We were considering how this it was a steady state signal, had a periodic nature. We were considering how the output would have, roughly speaking, the same nature. We were able to show it through all those derivations through Laplace transfer functions, and replacing Laplace variable with the frequency variable, this kind of stuff, right? Well, that is what we were doing. Now, what we did, in fact, during the lecture might have sounded quite complicated, right? But what we were trying to achieve was relatively simple. Like you get a sinusoid as an input, and you will have a sinusoid as an output. There is no way around it, right? It's always going to happen as a steady state after the transient processes go away. The only question is how the how the phase of the sinusoid will change. So how it will shift and how much its amplitude will change, right? So simple questions. The answer was complicated, right? We had to do, I think, 4 different pieces of mathematics to get to this answer, to do the border plot. Now, I think quite often when we do control theory, we somehow assume that those pieces of mathematics imply fundamental difficulty in the question, right? My previous lecture might have given you an impression that what we were doing was a deep math that is like outside of the realm of engineering. Something that you do not want to do yourself, something that you only seen once, believe in it, good. That I don't think is the case. I think the question itself is also more or less as simple as the question is simple, the tools are also relatively simple. So today what I want most of all is for you to see how the tools we are going to use are relatively straightforward and simple. We're going to address questions of input, this time both static input, so just a constant line, and periodic inputs, but without going through all of those transfer function mathematical stages, all right? So if we are lucky, what you'll see from this lecture would be sort of a sense of simplicity of the process. All right, let's get into it. We'll see what's going on. Oops, my apologies. Okay. So let us first start with a relatively simple example. We'll consider a ordinary differential equation with a constant input. All right. So I think we are familiar with the ideas. So here's ODE in this form, right? Now the input U is a constant, all right? Here, the right-hand side, I write in this general form where the input itself is differentiated as many times as we want, m times in this case. This is like this form, while maybe feeling to you slightly strange, we have seen it during the part of the course where we studied transfer functions. We saw how natural it is. This form also, from the same part of the course, you probably recognized as something that naturally arises when you have a tracking trajectory, when you have a controller, like PD controller, for example, that attempts to track a input signal, like a trajectory. So this is not a crazy way to describe something. It's normal. But in this case, when I say constant input signal, I mean U is constant, right? It happens that it implies that the whole right-hand side is also constant. This just happens to be true. But specifically, what I require to be constant is U. Okay. Now, since all of those guys are differentiating a constant, they will go to 0. And what we'll have is only b of 0 times u. But u is c, so it is b of 0 times c. The left-hand side stays exactly the same between two equations. Okay. Now, what I want to ask is, what is the steady-state solution? I will propose that for a stable system, if this ODE is stable, steady-state solution is going to be a constant. So this is going to be y, which is a constant. Please notice here the trick that I'm doing. I'm proposing a form of a solution. So I'm not trying to prove that the solution is going to be constant. That would be a different mathematical way to arrive to the same thing. What I'm doing is I'm giving you a theory. I theorize that the solution is constant. If I can provide solution that is constant, that would actually fit equation 1, then my theory was correct. If I couldn't provide it, that does not imply that there exists no solution. It just implies that I couldn't do anything with my theory. All right? Well, this way of doing things is very useful when trying to solve for particular solutions of differential equations. Often enough, you can predict the form of your solution. So you can simply theorize that the solution will have this form, and then the game becomes just to find constants in your predicted form. All right, so in this case, I predict a constant solution. This would imply that this equation here would lose every single member that is differentiated. So nth derivative goes away, first derivative goes away. The only thing that is left is a zero derivative. So a0 times y, since the solution is constant. Okay? And the right-hand side, you remember, is just b0 times s times c. So b0 times c. This way, you can find that as long as the solution is y steady state equals to b0 divided by a0 times c, which is your input, then this is a valid steady state solution. Just to double check, I mean, the way I derived it already checks that it is correct. But let me just, for your benefit, double check that this is correct. So right-hand side, as we said, if you substitute c there, which is constant, it will become b0 times c, right? Left-hand side, if you substitute b0 divided by a times c, what's going to happen? Well, this goes away, right? Because when you differentiate constant, it is 0, right? Same as here, this went away, right? And what we have is A0 divided by A0 times B0C equals to B0C. So checks out, right? So notice how I arrived at the solution. I proposed a form, computed the constants for this form by substituting it into the original equation, and then I got a valid solution. It's very good way to do things. Right. Now this quantity here, K equals to B0 divided by A0. We call it a steady state gain of the system. So what does it mean? It means given the constant input, let's say a step function, that is a typical constant input considered in control textbooks. So a signal which was 0, presumably back into towards minus infinity before the experiment starts. As the experiment starts, it becomes 1 and stays 1 until infinity. Yes, the question? Okay. All right. My apologies. Okay. So this is a steady state gain of the system, something that tells you how much the steady state input is amplified. So you put constant 12 volts through your motor. What is the angular velocity that you're going to get after transient process is over? The answer to this question is what is the steady state gain for the motor, right? You're going to do the same, for example, for let's say in airplane, you put some sort of signal through a control button, like, and you want to measure, let's say, the elevation of the airplane, right? Of course, here the airplane is a simplified example, and maybe not the great one, because almost everything there tends to be a result of like interactions of subsystems. But you know, at least with the motor, I think it is quite clear, right? What is the steady state gain? So if you have a constant input, which is going to stay constant, you want to have to see what is your constant output is going to be like. The difference between them, the ratio between them, is a steady state gain. All right, good. Next, let us do the same, but in a way which you would find in a textbook. So what I did just now, I think I'm not sure if you would find it in a textbook. Maybe not. Maybe not. But what I'm going to show you on this slide is definitely from a textbook. So consider transfer function. So the same system G as, let's say, on the previous slide is represented by a transfer function, right? Now, this here, you can recognize it used to be right-hand side of our equation, but now in Laplace form, it is our numerator of our transfer function. This used to be left-hand side of our differential equation. Now it is denominator. Okay. So I want to find steady state solution to the system. So if you allow me like sloppy approach to mathematics here, I would say that steady state solution corresponds to the moment where every component of transfer function that has Laplace variable in it. So every component like this of this sum, which is multiplied by a Laplace variable, goes to 0. Roughly speaking, when Laplace variable itself goes to 0, right? I say sloppy because I do not prove it to you, right? I give it to you as a somehow like intuition. You can instantly see why this would be valid, right? Because I'm canceling exact same components as I canceled previously. But here I would have to do some kind of proof to to explain why they have to go to zero for when we consider steady state solution. All right, I will avoid this for now. I would, you've seen motivation on the previous slide. And what you would notice is, as long as I would be able to prove to you that this is exactly what's going to happen, like for steady state solution, you need to consider a Laplace variable going to zero. You would find that the only members that are left are B0 and A0. So the gain, steady state gain of the system would be exactly the same. It would be B0 divided by A0. Now, you get two results from those two slides. And I don't mean that you got the same result twice, this result and this result, right? They are actually the same, right? What I mean is, one result, you now know what steady state gain is, you know how to compute it, you know how to derive it. Good. Result number two is, hopefully you can see that sometimes a relatively complicated looking argument in Laplace form can be replaced with a relatively simple looking argument in differential equations form. The differential equations seem to, as long as you're willing to think about particular solutions, seem to allow you more intuitive way to discuss the same problem, right? That is not to say that Laplace form is worse. It isn't. It is just, I think the amount of intuition that you can gain from this slide is slightly higher than from the next one, right? From this one. That is the second result. I would like you to sort of keep that in mind. All right. Is there any question? No? All right. Good. Let me go on a little bit. Well, just for exercise, do the same thing, but now with the state space representation. State space representation, we can also find steady state gain. How do we do it? Well, here's our steady state, state space system. And we want to find how the output would look like given constant input, right? Well, we theorize that the state of the system is going to be constant given a constant input. If it is a stable system, this is, again, a reasonable assumption. What's going to happen then is we would have, instead of u steady state, instead of x steady state, instead of x dot, 0, instead of x steady state, we're going, instead of x, again, x steady state, instead of y, we'll have y steady state. If x is constant, y is constant, because C matrix is a constant matrix. It is an LTI system, independent of time, so this will be constant if this is constant. All right, but now notice that from this equation, we can actually try to compute x steady state. If A has eigenvalues which are non-zero, like there is no eigenvalue that is 0, or, if you want even like more restrictive things, consider that has a real non-repeating eigenvalues, something like this, or real and complex eigenvalues but not repeating, and none of them are 0. Well, it would be full rank. It will be full rank. If it has no 0 eigenvalues, you can imagine you would have, the determinant would not be 0. You can try to prove that. If you have also non-repeating eigenvalues, like one of those nicer cases, you can instantly describe it where it's eigendecomposition, and you can actually find inverse that way. All right. So it would be full rank. It means that it has inverse. So we can invert it, and we can find x steady state to be equal to, there will be b and u, and multiplied by a inverse. That's what we are getting. That's what we are getting. So the only thing that I missed here is, I believe, minus sign, right? Take it. Minus sign. Right? So we put x to the left-hand side, multiply everything by -1, multiply everything by A inverse, we get this formula. Now, this formula we multiply by C to get from x to y, right? If this is the formula for x steady state, to get y steady state, we need to multiply it by C. So that's how we get formula 10. You can see here is a description of what x steady state is like. It's a minus sign. Multiply by C, you get y steady state. Now, this is a steady state gain for a state space system. Now, please notice it is not the same as in the last two slides. It looks different. Can we prove that it will be the same exactly? Yes, we can. If all three system representations represent the same system, it will be exactly the same. And how you would prove it? Well, you would look at A matrix. You would notice the structure of A matrix would be a lot of zeros and ones on top, one line of coefficients on the bottom, right? And B matrix would be 0, 0, 0, 0, and 1. C matrix would be, let me not make a mistake. I believe it would be 1 and 0, 0, 0, 0, right? I think so, but that's not critical. So when you do all of this, you would find that this multiplication here would lead you to exactly the same thing. It would lead you to A0 to the power -1 and times B0. So that's how you would prove. If you want to prove that same system but representing state space would give you same state gain, you can actually do it. But that is not the point here. That's not the point here. The point is, this is much more general. Previous results work for only single input, single output system, all right? Seesaw, single input, single output. This works for multiple input, multiple output. Your steady state gain is now not a number, it is a matrix. Doesn't matter how many inputs you have, doesn't matter how many outputs you have. You can compute steady state gain for all of them. You understand? Now, you don't have to compute it for outputs. You can compute it for states. So let's say you care about how the states of your system react to input. Like you want to say, how much does this velocity react to this particular component of U? Well, you just compute this part of the steady state response. So instead of computing Y steady state, you compute X steady state. Take particular part of this matrix. That's your answer. That is how much your U influences your particular X, right? You can ask all kinds of questions, like, for example, what is the worst possible input in terms of steady state gain? So what is the largest, what part of your state space would react worst for which input? You know? Or like, what is the worst input in terms of the reaction can produce in your steady state space? All of this is possible to ask using simply linear algebra. We'll do a little bit of this late in the lecture, so I'm not going to go into details here. But you can see that with this representation, not only did we avoid the mysteriousness of transfer functions, basically we were able to be as straightforward as with ODEs, right? The straightforwardness is about the same. But more importantly, we generalized. We can now naturally get the whole steady state input to output matrix for a MIMO system. And we can do all kinds of analysis with this matrix. So it is not only a question of what gives you more intuition. It also is a question of how should I put it? Of what gives you immediate tools that are immediately useful. All right. Good. Questions? No? Okay. Now, okay. Here, I actually forgot my own slide. Here's an example of how this guy transfers to the same steady state game. Let me just quickly show you. Right. This is an example for a particular 3x3 system. Right. We'll just quickly see what happens when you invert this matrix. All right. You get this guy. That is how inverse of this matrix looks like. You can just trust me. Double check after the class. We multiplied by B matrix here, right? And by C matrix here. So this multiplication, basically multiplication by a column vector like this, selects this column and multiplies it by B0. On the other hand, multiplication by this row vector here selects this row and multiplies it by 1. So you can see that everything else is going to be 0. And the only thing that is actually selected is this guy here. It's going to be multiplied by B0. So we have minus B0 divided by A0. This minus sign here will cancel this minus sign. So they're going away. And you get a steady state gain, B0 divided by A0. Exact same thing. All right. Now to interesting part. All right. Now to the interesting part. So far, all of this was relatively simple. I think maybe like perfectly understandable either way, whichever way we do it. Now let us tackle something that is much more complicated. My goal for next, I don't know, half a dozen slides will be to do what we did with Bode plot, but using only state space representation. So we'll avoid doing transfer functions and achieve understanding of how input response works, but using only state space representation. This is going to be important. It will give us additional tools which Bode plot does not give us. And I think even more importantly, it would give us understanding, like transparent understanding of what exactly goes on with this analysis. Right? So let's try to persevere through the slides. Okay, so we have input U, which is, as before, a harmonic input. So constant times cosine omega t, constant times sine omega t. So alpha cosine omega t plus beta sine omega t. That's our input. In this case, notice I consider a scalar input. So it's going to be seesaw, single input, single output system, to have a similarity with Bode plot. All right. Now, steady state solution here I propose would be given by xi. So individual component of x would be gi constant cosine omega t plus hi constant sine omega t. All right. That is what I propose. Derivative of this x will be x dot. And when we differentiate right-hand side, like this guy, what we get is, let me, I guess, use color coding a little bit more carefully. So what we get is omega, because those trig functions have omega under them, right? Hi cosine omega t, because we're differentiating this guy, right? Minus omega, again, there's omega here, minus gi sine omega t, because we differentiate this guy. The minus happens because derivative of cosine is a minus sign. Okay. Lastly, I'm going to say that output will have the form q cosine omega t plus r sine omega t. Notice that as long as you can find q and r, you are done. You are done. You only need to find them as functions of alpha and beta. So given a particular input with a particular alpha and beta, what gives you information about its amplitude and its phase. If you can find Q and R, you know the amplitude and the phase of the output. Then the difference in phase is your phase shift. Difference in amplitude ratio of the amplitudes is your amplitude response. That's it. So we need to find Q and R as functions of alpha and beta. Okay. Now, next step is going to be a little bit difficult, so let's prepare to it. What I'm going to do, that is the second trick I'm teaching you this class, is to group terms in front of cosine and to group terms in terms of sine in front of sine. Why is it valid? Well, you can imagine if cosines cancel each other, like, how should I put it? When you substitute these guys into here, what you want is for equation to become equality, all right? Equation to become equality. Now, this will naturally happen if cosine terms cancel each other and sine terms cancel each other, okay? And that's what I'm trying to do. So I would collect terms in front of cosine and rewrite this equation using only them, right? So I would just assume that cosine terms cancel each other, and I'll group them together. So let us first consider this guy, x dot. Where are the cosine terms? Well, the cosine terms are here. That is a cosine term. So omega times hi. Well, if hi, we group it into a single vector. That's what we have. Omega times h, right? All right. So I'm not sure if this is obvious, but x is a vector, right? So each component of x has a one cosine term. Here you can imagine that this description here, equation 15, is a description of one element of a vector, and there are like n elements. So equation 15, you can think of it as x dot 1, x dot 2, x dot 3, x dot 4, and so on and so forth, like this kind of vector. Each of them has exact same cosine term. So cosine term you can just put outside of this equation. So this vector will become just omega times h vector, like omega h1, omega h2, omega h3, omega h4. So when you put omega out, you get this omega times h, vector of h. Is this clear? Well, if like we have any unclarity in this stage, like let me know. Please stop me as soon as you feel uncomfortable. Okay. Good. Now let's consider this guy. Where are cosine terms here? Oh, clearly here they are. Here they are. Now we multiply them by a, here we get G vector multiplied by A, and that's it. That's the contribution. I guess for maybe to understand this a little bit better, if you don't like this idea of grouping cosine terms, if this is somehow a little bit complicated, think of it as we assume that sine terms do not exist, right? That they are cancelled by a different mechanism. They cancel each other somehow. Then what is left of x dot would be omega times hi cosine, right? What is left of x is g cosine, right? Well, x is multiplied by a, so we have a times g. X dot does not multiply by anything, so we get omega h. Cosines themselves will cancel each other because they'll be in every term. Okay. Now bu, what does this guy have? Well, this guy here has a cosine term as well. This is a term. This alpha cosine. So we have alpha here multiplied by b. That's how we construct this equation. Now here is we also need the same process. So y would be q times cosine if we only group cosine terms. Right? That is y. And x, when multiplied by c, here is a cosine term in x. Multiplied by c, you get c times, this is a cosine term in x. When multiplied by c, we get g times c. So you can see, I could have written 17 with cosines in every term, but they cancel each other effectively. Right? Okay, good. Now, doing sines is exactly the same. So I will only briefly show you what's going on. So this guy gives you this guy, right? This is here, a times h sine omega. This element times b gives you this guy. This element r is the same as x multiplied by c. So that's how we group sines. Now, what I want to convey is if both of those equations are somehow correct, then what happens is when we substitute this solution into this equation, elements that have cosine will cancel each other, all of them, naturally, because of this equation. Elements that have sines in them will cancel each other because of this equation. So this will become equality. That is the idea. That's the idea. That is why this works in terms of solving equation. Now, for us, the key result is that we went from a differential equation to a system of two linear equations, or two systems of linear equations, right? So we went from differential to linear. That is a gigantic result. Now, let us reap the benefits of this transformation. We do it by rewriting the same thing, but in terms of one equation. So those coefficients, g and h, they appear on both sides. We group them only on the left-hand side. We get this guy. Coefficient on alpha and beta are multiplied by this matrix. Right? And this last equation becomes this. Right? Now, let me just brief, maybe you mistrust this construction. Why does it look like this? I'll just quickly show you the previous slide. Good. So notice where does this come from? In this equation, we have h omega minus ag if we put everything to the left-hand side. In this equation, we have minus omega g minus ah, right? So we can expect when we take h and j out of the brackets, we would have omega I is identity matrix, minus a, something like minus omega I minus a. Except, of course, the order in one of them would have to be reversed because it's going to be either hj or jh, like when we multiply, put it in the matrix form. So let's look here. Yeah, and that's like jh is the form. So we have a times j, so it's minus aj plus omega I, so this omega h. So that's a cosine equation. And that comes from the sine equation. This construction is just b times alpha. This is just b times omega. So again, from those equations, this is just q equals to c times g, r equals to c times h. So this equation may look very strange to you, very big, very scary, but it is just two linear equations grouped together. That's all. And we can easily solve it. We just invert this matrix. We invert this matrix. We hope that it is invertible. If it is not invertible, we have some kind of big issue. So it should be invertible as long as there exists a solution to the system, right? But let's assume it is invertible. So what we get is now a solution to those conditions. Equation 20 tells us how the state reacts to the input. It's not the output reaction, it is a state reaction. So with this equation alone, we already know the solution to the differential equation. Basically, we substitute those g and h into the original equation. We get our solution. So we solve the differential equation for the particular solution. And we know how each component reacts to the output. But what we asked is how to the input. What we asked is how the output reacts to the input. So output equation is here. So we have to substitute our, instead of GH here, this equation. And that's what we get. That's what we get. Right? So instead of GH, we substituted this guy. That's how we get it. Notice this is a little bit similar to what we did in the slide on state space steady state gain. All right, okay. More importantly, this is a linear relation, and this is a matrix that maps your input variables to your output variables. So you can easily find output variables based on input variables. Just compute this matrix. That's it. All right. Notice no transformation into Laplace. No Laplace transformation, no transfer function representation, no fractional expansion, no inverse Laplace transform, no use of theory of complex variables, simple linear algebra. So in case you wanted to do control theory without knowing what we call TFKP, right? Without knowing Laplace transformation, everything else, it's still possible. Still possible. It just would require this type of linear algebra. All right, good. By the way, if at this moment you are asking where is the catch, why this is not in the standard textbooks, the reason is this guy. -1. Inverting matrices used to be always a very difficult process before computers. It was time consuming. And Laplace transforms and plotting body plot in the transfer function way does not require anything like that. So this operation for us it is extremely easy because we do it on a computer using modern algorithms, which are computationally expensive but precise. Back in the days when people were doing control theory, establishing all the rules of the subject, there were no computers that could easily crunch big matrices like that, etc. So this would have been perceived as a wasteful approach, like we compute gigantic inverse matrix for no reason. Right now, for us, it is we don't care. Like we have computers to do it. So this approach is viable now. It would have been wasteful in the 1980s or 1960s, something like that. That is my perspective on this. Of course, perfectly possible that there is like way more to to why people prefer even to this day to teach body plot using classical tools. All right. Now this matrix, I'll call it M matrix. It is a function of frequency. So this matrix is a function of frequency. It is not just one matrix. For each frequency, it is different. Now let us define the input coordinates as zeta, all right, as zeta. And the output coordinates we'll define as p. So p is equal to m zeta, all right? P is equal to m zeta. Because, output was equal to m times input. So input is now zeta, output is now p. So now what we want to find is amplification. So amplification is given as a ratio between the norm of the output, right? The norm of the output here to the norm of the input here. Okay. But that is the same. So this is just by definition. But this is the same as taking a norm of this p vector, right? You can see the form is exactly the same. And divided by the norm of this input vector, right? I would like to know for you to notice that these equalities here, they're not banal. Let me explain. The reason this is here is because this is how we define amplitude gain in the lecture body. And why did we define it this way? Well, because for a periodic signal, its magnitude will be defined in this way, right? Like this is how you find amplitude of a periodic signal. And you can link it to complex variable representation of a oscillatory motion. Then this will become linked to like how you go to polar form in complex variables, or even simpler, if you remember the very beginning of the previous lecture, in the polar form of a periodic signal, this quantity here, square root of those two numbers, was the radius of this polar form, right? So the amplitude. That's it. So this comes from considering the relation between two representations of sine waves, one through constant times sine plus constant times cosine. Those two constants are like coordinate representation. Or you can have amplitude and phase representation. Well, the relation between those two is this expression here, square root of x coordinate plus y coordinate, right? So that is where it comes from. Now, that is where this comes from. But it just happens to be the same as a norm of a vector. So that's what I want you to see. It's not that we decided to compare the norms we know that that's what we want to compare, and it happens to be the norm of a vector. Okay, right. But the norm of this vector, vector p, happens to be m times zeta. So the vector p happens to be m times zeta, so it is the same as the norm of m times zeta. Now, here's a piece of math that I don't know if you studied or not, but when we deal with these things, there is a natural connection to a matrix norm. So our task right now is to find maximum amplification. For a second, we'll assume that we want to find maximum amplification. Of course, like in reality, amplification is the same for all inputs. Like it is not the question of like this phase shifted signal would give you one amplification, this phase shifted signal would give you different amplification, or that amplification depends on the amplitude of the input. None of this is true. Amplification is constant, right? But we can, since it is constant, it does not depend on a particular zeta. We could still ask ourselves, what is the maximum possible amplification for any given zeta in this scenario, right? It just happens to be that maximum minimum are the same, but we can still ask what is the maximum value of this amplification given zeta, for zeta. This happens to be equal to a second norm of a matrix. So this is a definition of second norm of a matrix, right? I'm not going to prove it to you right now, but it is a fact from linear algebra. When you see this type of thing, like matrix times vector, second norm, divided by vector, second norm, the maximum possible value that this ratio can attain is a second norm of a matrix. That's how we define it. We call it induced norm for that reason. Okay. Now, this induced norm, it just happens. It's very easy to compute. It is the largest singular value of m. Largest singular value of m is the second induced norm. So singular value you compute by singular value decomposition, SVD, and you get the first constant, the first number out of this SVD decomposition. That is your largest singular value, right? The first element on the diagonal of the diagonal matrix in SVD, if that's how it is easier for you to see it. Yeah, largest singular value, largest singular value. Okay, so somehow we were able to find this part of Bode plot simply like this, largest singular value of this matrix. Again, no Laplace transform needed, no fractional expansion, nothing. Just write this formula, crunch this number, you're good. Okay. Next. Just for sake of interest, I will show you how phase is computed. So phase as a function of omega is the difference of the phase of the output and the phase of the input, which is the same as phase of m times input minus phase of input. M happens to be orthogonal matrix. Orthogonal matrix. Orthogonal matrices are the ones that rotate everything. They rotate the input signals by a fixed amount, right? So they do not scale. Can I say this? Like basically it is orthonormal matrix scaled by constant. Okay, let's be more careful because orthogonal matrix can scale in general. This orthonormal matrix, so orthonormal is here, but scale by number. That is actual form here. That's actual form. So it is basically a rotation matrix, 2 by 2 rotation matrix. It has to be 2 by 2 because there is input is 2, the output is 2. Scaled by a number, right? That's what it is. And this rotation matrix just rotates everything by a fixed value, or fixed angle. So this difference would simply be this angle phi. And how do you compute phi from there? Oh, by finding, for example, arctangent 2 between this number and this number, right? How do you find angle of a given rotation matrix? The classical question. This is quite easy. Like this, you can see as a vertical projection of the same vector of this column vector of the matrix. This is as horizontal. That's why you can do arctangent 2. Right? So we were able to do Bode plot without doing Laplace transform. Is there questions before I move on? Okay, if there are no questions, let me point out a few complications. So first of all, this Bode plot, naturally the phase here would produce whatever arctangent 2 produces. Classical Bode plots prefer to have uninterrupted flow, right? When we analyze Bode plot, we don't like the 360-degree jump, where after 360-degree, we go to 0, That's not what we like. So plotting it this way would, in practice, encounter some difficulties. To combat those difficulties, you can just use software to plot Bode plots. Like it doesn't matter to you how software is organized inside. To you, what it produces good Bode plots. So you don't have to do this stuff by hand. That's not what I'm trying to teach you. I'm not trying to teach you to skip control libraries and write stuff by hand. That's not the point. My point here is to show you that all of this can be done as a linear algebra, which you should understand. Like it is perfectly acceptable if you, as a specialist later on in your life, feel like Laplace transform is a complicated mathematics that you don't want to mess with. Acceptable, right? Linear algebra, you should always be comfortable with. That is your bread and butter. So you cannot feel uncomfortable with linear algebra. And all of this, sorry, my apologies. There's a little bit of technical mishaps today. All of this, what we saw, like this is linear algebra. So you should feel comfortable with it. And this means you should be able to understand what's going on inside Bode plot. Not just use Bode plot, but understand what's going on inside. That is the point. All right. Also, I did not prove to you that this is so. I will leave it. I will leave it without proof. I will leave it without proof. If you're interested, good thing to try to work out. Right. Right. But everything else is proven. Like this guy, if you find this step strange, this is standard linear algebra stuff. You can open a induced matrix norm page in any textbook, even Wikipedia, you would find proofs for that. So this is not a strange piece of math. Right? Everything else is just notation. Like we did not do anything strange here. Okay, all right. I think we did quite a bit of work, but now let's understand why it was beneficial. So first of all, it was beneficial because we dropped the reliance on single input, single output. What we did works, of course, for single input, single output, as well as in the Bode plot. But we know how it does it, right? We know exactly what's going to happen with different inputs and different outputs. Well, let me go back and show you. So all of this, you can see here, relies on the fact that this y matrix, y value is a scalar, and this is a scalar. But we don't particularly care which scalar exactly is it. Sorry, what I was saying is this matrix we can replace it with anything else, right? Same as I guess as in transfer functions, right? In a sense. So we could try to see how the system would work with different C matrices or different B matrices. And we know exactly what's going to happen. This matrix here would go from being, this particular C to being a different C, from being this particular B to a different B. That's it. So we can see how all of this changes as we go from input to input. In fact, what we could do is the following. Let me show you. We can ask a question. Let us consider fixed input matrix, right? Which output, considering its norm is 1, produces largest amplitude of the output signal? So what we are going to ask is, in the whole state space, which slice of this state space is responsive to the input in the worst possible way? So imagine you have a complicated system, hundreds of inputs. You can plot Bode plot of all of those states individually. But what if a combination of two states is excited in a way much worse than they are excited by individually? What if there exists a combination of states which together is very excited? It doesn't even have to be very excited. Let's say you are working on a system which works at certain margins of performance, right? At certain margins. And you want to make sure that your amplitude response is always bounded by something. Well, how can you be sure that it's bounded by something if you're only considering particular representation of the state space, right? It's good if your representation of state space actually is physical, right? And you can always put physical limits on everything. But if it is not like completely physical, if some of it is just a choice of coordinates, like let's say in the x coordinate we have this oscillation, in the y coordinate we have this oscillation. What about xy coordinate? What about diagonal? What if in the diagonal direction your oscillations are much worse? You can see, right? So we can ask a question: what will happen in the worst case scenario? What is the worst case scenario given a certain input? Let me show you how it's done. So from the previous slide, what we saw is that this is the same matrix, right? The matrix is described as amplitude times the rotation matrix. And this is this M matrix here, okay? Now I will introduce notation defining this guy here as P11, P21, P12, P22. Right? That's the notation I introduced. Additionally, I introduce notation defining amplitude of omega as M, small m. So this becomes small m. With this, our rotation, our left-hand side here becomes this, right? We have this small m appear in front of every single term, because of this, right? The right-hand side, on the other hand, becomes, let me use different, becomes like this. So this was the right-hand side, it becomes like this. Basically because we multiply by C, this like a row of C's, we multiply all of those guys, right? And by these rows of C's, we multiply those guys. Am I saying it correctly? Let me just double check. Yeah, I think I'm saying it correctly. Yeah. So we basically, it is a diagonal matrix. You can kind of believe me that this is what's going to happen, but it happens to be true. All right. So what we have is this guy is now written like this, okay, with a new notation that we introduced. What we can do next is What we can do next is we can consider the elements of this matrix on the right. So I will have to try to be careful. It's going to be a little bit difficult, but if we take this element, right, which is the same as this element, right, we square it. So we find its square here. It will be the same as the square of this element. So the element multiplied by itself. So m squared cosine squared is now equal to c times p transpose times c transpose. Right? We can add to it. Sorry, I'm trying to use color coding, so it's not completely crazy. We add to it, let's say, this element, which happens to be this element, squared. So it is going to be m squared sine squared. So it is c p21 transpose c transpose. Right? It's the same as this transposed squared. Notice what we did here. What we did here is a trick where we got a sine squared plus cosine squared, which we know is equal to 1. So we get m squared here. Now, what we get on the right-hand side is we get a matrix. Okay, I will just use more color coding so you understand what's going on here. Let me try. We get a matrix multiplied by c on both sides, plus a matrix multiplied by c on both sides. We take c out of the bracket, so we get this matrix multiplied by c on both sides. All right, so this expression 29 is just m squared equals to c times this big matrix times c. But m, remember, m is our amplitude. So what we wanted to find is the worst case scenario in terms of amplitude for all possible C matrices. So we want to find such a C matrix which will produce the worst possible output. So equation 29 gives us equation which relates C to the square root of the amplification. That is so far as we went. Let's continue. One more slide. And here I will just define this matrix as M for simplicity. And we can decompose M by what we call square root decomposition. So N will become D times D transposed. Okay. If this sounds crazy, it's not crazy. It's just part of eigen decomposition, if you want. Like if a system if a matrix has, eigen decomposition, you can always do this kind of stuff. All right. So let's say we have this decomposition. Now, next, what we do is we consider M as a maximum. We try to find the worst case scenario M, which is the maximum over C of this guy divided by this guy, right? What is this guy upstairs? That is just C times this guy, right? Times C, okay? It happens to be equal to square of M. So what we care about is not square of M, but square root of, but the M itself. So that's why square root here. Okay. And we divide by norm of C, just so the increase of the size of C won't matter, right? Okay. Now, what happens next is this upstairs stuff is the same as the norm of this vector, right? Because it is basically this vector times itself, square root. So that's the definition of what a norm is. So we have this guy. And we saw it previously already. This is just the biggest singular value of this matrix D, which happens to be square root of the biggest singular value of n. So at the end of the day, it is just the biggest square root of biggest singular value of this matrix. Now, you can tell me very easily that all of this was very complicated and not easy to understand at all. And I don't disagree. Like, this was complicated. I think, this part was relatively straightforward. With some things that are difficult, but, relatively straightforward. Here it was just a lot of math very quickly. Maybe you have objections about it. Maybe you can object to this decomposition or whatever. Like, it's not straightforward. But, it is worth it, is what I'm trying to say. It is worth it. Let me show you why. So here is a system. I just generate the system. Here is a Bode plot. There are actually two Bode plots there. One is plotted by algebraic method, another one by MATLAB, a built-in tool. Right? Now this dashed line here is a worst case scenario Bode plot. You can see it is clearly above the other one. So what I'm trying to say here is, if I only considered this one Bode plot, I wouldn't have caught this worst case scenario. Of course, we can discuss like what would have happened if I considered all possible Bode plots, etc. How much worse this worst case scenario is than the average, etc. There is a lot of conversation that we can have. But you can notice that at least in this example that I'm plotting here, this worst case scenario clearly is on top of the Bode plots they plotted for a given input, right? So for practical use case, this might be interesting. This might be very interesting. I feel like sometimes people don't use Bode plots for MIMO systems because they think that it is just a single input, single output tool. Like the tool is only for seesaw systems, where it works for MIMO just as well. And for multi-input, multi-output systems, there are additional questions to ask. What is the worst case scenario in terms of amplitude? And given a fixed input, what is the worst case input? What is the worst case amplification in terms of state? It's like you have all those possible inputs, all those possible outputs. What combination gives you the absolute worst? Good question, good question. And all of this is a matter of linear algebra. Like, you can do it with linear algebra. So you don't have to invent all new parts of Laplace theory, like transfer function theory, etc., to ask those questions. It is linear algebra. So everything is invented already. That was my point with this lecture. I wanted you to see that all of this stuff is not magic of like difficult calculus. It is straightforward stuff that you can actually use in practice, and you should. Right, now we have last few minutes in the lecture. My apologies for the horrifying quality of this picture. So I did not expect it to compress this bad. All right. Hopefully you can still read what is written there. Next time I promise better quality. So what we did so far is already taking us quite a few steps forward. First of all, with those last lectures, we already saw what seesaw and MIMO means, right? We noticed that when we discuss, for example, Lyapunov stability, it is irrelevant if it is seesaw or MIMO. We can do both at the same time, right? It doesn't matter because we use eigenvalue criterion for stability, which is natural for MIMO systems. Actually, input and output for Lyapunov stability is not important in itself because it is a quality not of, it's quality not of inputs and outputs. It's the quality of the system itself, right? Okay, good. We notice that Lyapunov stability can be solved using static feedback. So we could just produce a controller in the form U equals to Kx, and we solve Lyapunov stability. All right. For producing those controllers, we can use any of those. Like, for example, ODE was very useful for PID controller stuff, PD controller, right? State space was useful for discussions of pole placement. I believe MATLAB instruments for pole placement work readily with state space, but they would also work with transfer functions. Okay. What else we found is that it matters what inputs we have. So given a single input, single output system using transfer functions, Laplace transforms and stuff, we can answer how we respond to periodic inputs, right? How we respond to periodic inputs. And this is done by Bode plot. We can answer how we respond to steady state input. And this can be done using transfer functions, but also I showed you how to do it in state space and using ODE, right? And even periodic, you can also do in state space and it's state space form. As I showed you this time. So this discussion of single input, single output systems is limited because because of the nature of our analysis. Like Bode plot is a plot that naturally plots how one input affects one output, right? That is the reason why we use seesaw for periodic, but it is not because of some fundamental limitations. Like we could do the same in MIMO. Same with all three representations. There is no fundamental limitation why we have to do it in transfer functions. I showed you that we could do it with a state space, for example. Now, there is quite a lot left to discuss. Like even here, we discuss periodic. Notice that there are aperiodic signals and more to come, right? These aperiodic signals, you can imagine like something does not have to follow a sine wave. It can be decomposed. If it is a finite time, you can decompose it into sine waves, which is, might be a good answer to this question. But not everything is periodic, and not everything is limited to static feedback. And even the forms of the systems that we considered so far does not cover everything that is being used right now. So I think this lecture kind of closes the first half of the course, where we were struggling to get the idea of what control theory actually does, what control theory works with, and so on. Now you went through this. Now you know. Now you know this representation stuff. You understand the terminology. You understand the basic goals, right? You understand the basic tools. Later, what we'll cover more advanced stuff, such as discrete systems, such as filters, systems controllers with something that you can describe as memory, so with internal states, and so on. It is going to be more advanced, but also it's going to be very useful. Mathematically, though, I'm not sure if it is going to be more complicated than what we saw so far. So don't worry, the complexity of the math is going to stay about the same in the second half of the course. All right, I think that's it for the lecture. I will stop the recording and you can ask questions if you have them.